Welcome to all you that have come down to TE Studio for the event. Thanks for coming. Just want to make sure questions are up. And thanks for everybody who's online with the webinar. Online, if you have any questions or if you can't hear, make sure that you type into the questions dialogue on your application and we'll make sure that it gets taken care of. Well, first off, I want to thank a couple of our board members for helping set this up. Peter Yackel over here, Tim Eian for letting us use his space, Ralph Jacobson, David and Jared, David Ann and Jared Cesara. I always screw up his name. That's close enough. But thanks for helping out, guys. Well, basically, we had a meeting the other day, one of our board meetings, and we were talking about projects around the country, and it had been a while since everybody kind of took a recap of what's been going on. So that's why I thought I would just put together a small slideshow here before Tim goes on, just to kind of bring us back up to speed, because the Passive House Convention was just last week in Pittsburgh for 3 days. Ralph spoke there. He told us good things about it. And so right now, Passive House Institute United States, they currently on their website, they have 89 registered projects, and that's probably going to be growing. And, in Europe, there's, thousands of projects registered and more that probably triple that are not registered. So I just want to take a few minutes to go through some of them. Let's see, advance. It's not advancing. Okay, there we go. So before we start looking at some of these example homes, I just wanted to have a brief overview. Tim's going to go into what is a passive house a little bit more later, but this I stole directly from Tim. It's kind of a short list of the differences between passive house, like solar. Sorry, the heater just came on. Solar passive design and passive house design. And basically, Tim will go through all these later, and I have these up there for reference. But this is what a traditional kind of passive solar house that we know, that we were taught in school, south-facing, a lot of glass, high windows in the center to have that stack effect, to have natural ventilation. Nothing wrong with these designs. They work. They're great. They just sometimes limit the architectural character that maybe you can't use everywhere, and it kind of forces you into certain site orientations. Not to say that our passive house definition doesn't need passive solar heat gain, but it's not quite as limiting. So with that, I'll just get into some examples, and you'll see here that there's a lot more variation in the passive house designs that are coming along in the country right now. So this first one I was just showing is BioHouse, which was actually designed by Intep, by Stefan Tanner in 2006, and it was the first certified passive house in the United States. So there's, and that was in Minnesota, so it's kind of something that our chapter always makes sure that we mention. Passive House in the Woods, was this the first certified in Wisconsin, Tim?
It was, yeah.
Right across the river in Hudson, Wisconsin. As you can see, it's got some south-facing windows, but a modern design, and it is a net energy positive and carbon neutral passive house. It's insulated concrete form construction with a stucco system on the outside. So that was kind of a big deal for this area to have a passive house built around here. Another project done by TE Studio, Tim's firm. This is one of the first retrofit attempts to be certified through the Enerfit passive house certification in Germany. It's here in Minneapolis. It's timber construction, stripped down to the studs, and then outside of the studs and the sheathing, the design called for 8 or 10 inch TGIs running vertically filled with cellulose insulation. And I'm sure for those interested, you can talk to Tim about it afterwards. And that was just completed last year, 2012.
Yeah.
This is the project that Tim's going to talk a little bit about, the 24th Street Passive House in Crosse, Wisconsin, commissioned by a Western Technical College down there. And they are one of the first project in Wisconsin to use Passive House as an educational tool. And they're going to try to create a kind of an example for urban infill neighborhood development. So this is an exciting project as well. This is a project out of River Forest, Illinois by Tom Bassett Delhey. The Lima residence. This utilizes insulated concrete forms as well. Um, I actually went through certification training with Tom, so it's great to see that he has been moving forward and building some homes. And it's one of the first passive houses in the Chicago area to be certified. This next house is by Dennis Wedlick out of New York. And I guess one of the reasons I'm choosing these projects is not only because as an architect, I feel that they have different characters to them. They don't all look the same, but they're also in different areas of the country to kind of show the versatility and what maybe passive houses look like around the United States because we have so many different climates. This was completed in 2011, and it's an extremely airtight house per the way that he designed it with some glue lam structures and SIPS panels on the outside of the glue lam with this simple form. It created a super airtight envelope of 0.16 air changes at 50 Pascal, which passive house standard is at 0.6, so quite a bit below that. The Karuna house, this is in Newburgh, Oregon, and here you have kind of this ultra modern looking residence, which I find attractive. Other people might not, but it is actually, Tim consulted with Intep here to be the first Minergy. It's passive house certified, but it's also the first Minergy certified house in the United States. And Minergy is a Swiss energy certification similar to that of passive house. So very cool. The spec residence, brought this example up because this house, if you're going down the street, I don't think you could tell it much from any other kind of suburban custom home. It'd fit right in, and that's kind of one of the great things I think about passive house design is that you can do it a lot of different ways, and it can be done for the masses. So, not that this house I think looks great. So it's out of Virginia by Quantum Architects. Our house, this is it's almost an experimental house for Syracuse University. So here's kind of a little modern facility, only 1,100 square feet, and it was a competition winner as part of a Syracuse neighborhood revitalization through the university. The Heidelberg Passive House here out of Pittsburgh, I chose this because they had achieved a construction cost of $225,000, which to the construction company that they work with was similar to their standard spec home that they build. So they were proving here that passive house doesn't have to come at a premium. It can be designing for the same amount of money as others. And then this Hill residence, this is a nice little house out of California, and it was actually named the 2013 Fine Home Building House of the Year. And in California, they don't have to insulate the same that we do in Minnesota and the northern climates. So, but nonetheless, it is a passive house, and it also is LEED Platinum. This Landau house out of Vermont was designed by Zero Energy and in collaboration with Bensonwood Homes. And what they're able to do is they're able to panelize the construction of their passive house here. So all of the walls and the wall panels were designed and built in a factory and shipped out to the site. So it really increased the quality of the construction and reduced any exposure to the elements for the wood and the timber in the construction. This house is out of St. Louis, Missouri, and it's the first passive house certified in Missouri, done by Butterfly Energy Works. And so it's another modern kind of design. And I think this is the last house I'm showing. This is a Habitat for Humanity house. And I brought this up because many Habitat for Humanity projects around the country are really accepting green design and trying to push the envelope. And there are a few of them that are doing it to passive house standards. This one out of Vermont. I guess I was wrong. I got another house. This is a student project for Studio 804 out of the University of Kansas, constructed in 2010. And it was designed and built all by students. And now, that's all a bunch of single-family residents. And I'm just going to run through 6 or 7 examples of some larger scale projects that are coming on works online here in the country. So to show that the scale can be made bigger. The Harrison Street Houses is out of Illinois, and this is in design by Tom Bissett, Delhey again. And the next few homes are done by Plum Bob out of Philadelphia. And this house actually, these are 3 row houses. And they were constructed in a factory, prefabricated modules stacked up to create these row homes. I think each one, it says 1920 square feet for each. So the scale is moving up here. That same company has in works the development for 27 unit townhome design here, and they have 3 of them built and there. And as you can see, I think they're about 3 or 4 stories tall. And I know it's just exciting for me to see large scale multi-unit development starting to go up to Passive House standards. Same company again, and then just kind of cranking up the scale. And this is in development. They're looking for investors. So this is, I think, modern timber construction over concrete. So trying to bring Passive House to more of a developer model. These last few projects are done by Quantum Architects out of Virginia. And I brought these up just to show that this that Passive House can be applied to commercial projects as well. This is a small schoolhouse, 3,600 square feet in Virginia. This next one is actually the largest Passive House in the country. It's a 40,000 square foot dorm at Emory and Henry College. It actually performs 74% better than code. And there's a twin to this dorm right across the street that was built conventional construction. And this actually, the design firm was able to bring it in under the cost of the conventional constructed dorm. So that was one of the big sticking points, and they hit it. And finally, the same firm, Quantum Architects, has designed a dental clinic in Virginia, and it is actually the world's first Passive House dental clinic. So, yeah, at a square foot cost of $155 a square foot. I guess that's really good for dental clinics to stay on par with traditional buildings. So, with that, this presentation will be along with Tim. So here's some of the references for you if you ever want to look up some more projects. With that, Tim.
Thank you, Jay. Great. All right, let's switch over here. Well, thank you all for coming. This is our office here. You can see me in this picture, and Stefan, my business partner. At Intep and T Studio, we focus on high performance buildings and building consulting, and we do that virtually on any scale. So we work with clients on very small projects. We do residential homes, and we scale up from there. And we do a lot of high-level consulting with cities, municipalities, campuses, and institutions to help them navigate basically their real estate and make it fit for the future and mitigate risks. So that's a little bit about us. I want to take just a couple of minutes too. There may be some people who are not completely familiar with Passive House, and just kind of reiterate what the standard is. So I'll give you just a 5-minute version here. Right now in North America, you really have 3 choices. They're listed here from left to right. You're looking at the FIAS program, which is the Passive House Institute in North America. And there are some ideas about making this more of a North American program and maybe varying some of the performance parameters based on location and climate zone. And we have obviously 7 climate zones and very distinctive climate zones in North America. So this is a response to the circumstance here. And so that's the one on the left. The one in the middle is the PHI logo, the Passive House Institute in Darmstadt. So this is the original or traditional Passive House, however you want to look at that. That's been around since the early 90s. And the one on the right-hand side, the EnerFit program, is something that the PHI came out with a few years back, first in draft spec and then in finalized version. It's geared towards retrofits of buildings. So obviously we have to recognize that there is a lot of build product out there that needs to be retrofit, and the Passive House's version of that is called EnerFit, and it is a little bit more lenient than the original new construction standard, recognizing that you can't fix all problems in existing buildings. And it has what I find quite interesting. It has 2 tracks. It has a performance-based track and a prescriptive track, and either one of them can lead to certification. So if you have a building where the conditions are just so limiting that you cannot hit the performance parameters for space heating or overall energy consumption in a year, they will allow a component-based approach, which means you're updating the insulation levels and air tightness in the home or building to a certain spec. And if you meet that minimum spec, you can get certified under that program. You can read for yourself the little descriptor down below. And again, it was originally conceived as a German program, so of course it is a rigorous program. I always make sure to stress that. To me, I think the part that's much more important is that it is a tool. And as a designer practitioner, it's very important that it acts in this way. There are many great building standards out there that are readily available, but there are few that provide you with actual tools and guidelines of how to implement that in the field. And so that's one thing that's great about Passive House. It comes with an energy modeling package called the PHPP, or Passive House Planning Package. And it's incredibly powerful if you're trying to make good and sound decisions about your design. And so that's something that I'd like to stress. And there are people out there who think it's more of a fad or sort of something you need to buy into. And I think I look at it much more pragmatically. It's really a tool, a utility that allows me to make better buildings. And the tool itself is useful even for buildings that are not passive houses or aren't geared towards that. A lot of the basic calculations it performs, they hold true for all sorts of buildings. And we sometimes make comparisons where we model conventional construction, if you wish, with higher performing construction. And we use the same tool for both approaches and generate meaningful results. I think it's also important to sort of put this on a map. So these bars, I hope they read well. On the far left, we have sort of conventional construction. That's if you hold yourself accountable to local codes. Certainly when I'm speaking to this, I'm talking more about what we have here locally. So Minnesota and Wisconsin are sort of the areas in which I do a lot of my work. So that would be my reference line. And then if you go to the advanced building programs that are out there, such as LEED or Green Star, most of them have a fairly modest energy improvement component. I think from what I hear about LEED, there's an effort to try to ramp that up a little bit, make that more significant. But in most cases, the advanced building, if you want, ends up being 10 to 30% better than the average building that is traditionally built. Not to say that there aren't outliers that go far beyond. The nice thing about Passive House is because it's performance-based out of the box, you're at a very sort of fraction of the standard or conventional construction. What we see with our buildings is that the overall energy consumption is reduced by 50 to 75% in the buildings that we've designed. And it certainly depends on what type of building it is and also how the users interact with the building. There are people who are more energy aware and some that are not. And it's essentially like driving a hybrid car, and you can do that carefully and hypermile it, or you can have a leaded foot, and that makes a difference. But out of the gate, Passive House tends to avoid about 90% of the heating energy and anywhere from 50 to 75% of the overall energy. And then just to clarify, net zero has become a really hot topic. A lot of people talk about it. So essentially that means that the meter that supplies you on your site spins forwards and backwards the same amount in any given year. So that would be a building on this scale here that has virtually no site energy footprint. And then there is life on the other side. We would call it a plus energy building, and that's for those people who want to either actively generate more energy or are interested in a carbon equation. Typically, anytime you're talking about carbon neutrality or carbon positive buildings, you need to go to the other side of this equation, and so you need to make an energy plus building. And so ultimately, in an extremely sustainable world, that's what we'd be doing, and some of those buildings could offset other buildings that cannot be upgraded to this level of performance. I apologize for the phone. One of the things that I think is always important, this is a graph that we made for residential scale projects, is that if you make the investment into a really high performing building, and in this particular case, we're sort of comparing net zero design with conventional design, you can really come out ahead over time. we can all agree that a better building will cost more money on day one, even though Jay had some examples where it's very cost competitive. But in most cases, and the climate plays a role here too, the more limiting the climate, the more you do have an upcharge to get to a better building. But eventually you come out ahead on pretty much all of them. And so this is really just about time. So when we're talking about cost, we have to look at time, and we also have to look at life cycle costs. So it's not just about saving energy, but it's also about making a quality building. And with that, we can avoid maintenance cycles or reduce maintenance cycles. And these approaches can have a compounding effect that can be quite profound over cycles upward of typically 15 years. Some commercial developers look for much shorter returns than that. And so there's certainly a lot of questions around, is passive house the right approach for short-term investment? I think it depends on where you are and how much of a jump it is compared to your baseline. But in general, it's fair to say that if you have 10, 15 years, you will certainly break even. And after that, certainly come out ahead. That's at least what we find with the designs that we're making. And so for the owners who take a mid to long-term view on real estate, this becomes a very attractive model very quickly. Just sort of on that cost note here, there's a couple of things that we've observed. When you're comparing a passive house building to what's conventionally built, we have to recognize that a passive house is a quality building. So we can't, it's the question is not how low can we go, but how good can we make it? And so there's maybe initially a cost increase in making a quality building. And from there, we saw in the past, and we've been able to, be on, lead this sort of movement here to some extent. So we've been there for some of the earlier days of passive house in North America. There is this paradigm of the lighthouse, and we saw those, buildings cost anywhere 10 to 20% more maybe than their comparison in traditional construction would have been. What we see today is, there's certainly a price to be paid to be an early adopter, and that's kind of the stage in which we are right now. And the outlook from Europe tells us that, with some scale, the upcharge can be very minimal. I do caution to get too hung up on this because there's many other benefits besides the financial equation here, and these numbers can vary greatly depending on where you are. If you're working with a team of people who has no idea what they're doing and they need to elevate their game to meet all these standards, those percentages may be meaningless. At the same token, again, going back to what Jay said, there are other parts in the country where it isn't as much of a stretch and the cost increase is almost negligible. So the truth is somewhere in between and all around. But what we're suggesting is that as contractors in particular become more acquainted with airtight construction and the diligence it takes to make a high-performing building, the costs certainly go down. And that's something that we see in our practice too, because we don't have to be maybe quite as diligent in how we document it if somebody's already seen it once or twice. I think one of the biggest parts here in terms of the cost is life cycle cost. So obviously you're looking at a model that is incredibly powerful over the cycle of the entire life cycle of the structure. So again, having a baseline building on the left, which is conventional practice, and a passive house on the right, we all agree that a better building costs a little bit more. So there's a tiny little dollar sign extra. On the operations side, there are some significant savings to be had. I mean, if we're talking about a 50 to 75% energy reduction, that's money back in your pocket, and that money has had traditionally over the last 30 years an escalation of about 6.5% per year. So that's something you can't even get if you put money in the bank these days. Maintenance, just because of the fact that this is a quality approach, the maintenance portion typically drops. You're using quality materials and technologies and processes to make a passive house building. So we see life cycle of product stretched and maintenance cycle stretched, and that helps with this. And then in essence, your total cost is essentially cheaper over time, and that's the takeaway from this here. I'll jump through this list here. I'm not a big fan of lists and reading them out loud, but this is a list that we made at some point to outline the benefits of passive house. And some of the ones that stand out to me, besides the energy part that we covered and the cost portion we covered, is really the comfort piece. And there's a slight health component connected with that. If you're more comfortable and if you have good indoor environmental quality, which comes out of the requirement for ventilation in these buildings and the high R values, then that's something I think that's at the end of the day also worth money in your pocket, but it also provides an owner of a company potentially with happier employees and more productive people, and somebody who owns this as a home just with more enjoyment of the space itself. And we've already covered that this is an approach that can be taken for commercial, residential, and retrofit. That's always important to note because it is so often associated just with homes. It's also a global solution. So at this point, it's found adoption virtually all around the world. And I'll show you just a couple of landmarks here. Again, Kranichstein in Darmstadt, this is the very first Passive House. It's a side-by-side fourplex. This is in the early 90s. And that is really ground zero for this movement. And that house, is still occupied, still operates beautifully today. And so for those people who are worried about, is this a fad or how do these things hold up over time? There's good precedent, with this building now being just about 20 years old for something that lives up to the expectation. For us in our office, and I don't want to dwell on this, but Jay showed these before, the Biohaus in Bemidji, still one of very few commercial buildings. And the nice thing here is that it's a school building. It was brought about through Concordia language villages up here in Bemidji. And so over the course of any given year, there's hundreds of students who rotate through this building. So the great thing about it is that there's exposure to young people. They can see how this all works and feel it. There's a dorm section on the lower level. 20 people can stay in there. There's bathrooms in there. And then the upper level is essentially 2 classrooms, and there's a little kitchen in there. So it's kind of a mixed-use building, if you want, with a fairly modest footprint. That building operates on 12,000 kilowatts of electricity in any given year. And if you compare that to other buildings that have that density of functions, that is actually a reduction of about 90%. And it does that in climate zone 7 up in Bemidji, which is one of the harsher climates to try to make a passive house. This was the first passive house that I designed. I think the point maybe worth making here is that this is one of those Energy Plus buildings. So the amount of renewable systems on that site actually offset more than the footprint of the home in any given year. And it's done that now in its 3rd year in a row. So we monitor that, we track that. For us, this was a great learning example to basically see how our design performs in the field. We have an online monitoring system actually on both this and the Biohaus, so we can see what these buildings are doing. So both of them have been sort of a lab, and they fall into the category of lighthouse in my book. I guess this next one does too. This is again the Minifit house. This was the first cold climate retrofit that the Passive House Institute has ever engaged in. Is going to show we still have the plaque here that needs to go on the house. So hopefully with the Passive House Days coming up, we'll be able to mount that. But this is great because it demonstrates the validity of the concept in an urban infill, and it leverages a structure from 1935. It preserves the look and feel of that neighborhood and of the original qualities that the building has had, and still turns it into an incredible performer. And just on a related note, I think 2 days ago, the owner posted on Facebook that obviously they haven't turned on the heat yet, but it was dropping slightly below 70, so it was time to bake some bread and do a load of laundry because those are great ways to heat a passive house. Global adoption, just a couple of pictures here. I was trying to get one from each continent, and so I think we have them all represented here. Also, one of the first high-rise buildings that was built to Passive House standards in the lower quadrant there, and a portion of a multifamily building that a colleague of mine did, and also some solar decathlon winners. So this can now be found virtually anywhere in the world. So with that, we get to the 24th Street Passive House. This project came about through some consulting work that we did for Western Technical College. This is a sort of a local college in Western Wisconsin. Has a lot of the trades as programs. So they have architectural technology, they have HVAC programs, they have framing programs. So they have sort of in their constituency and in their program, they have a connection with buildings. And one of the things that they've been doing over the years is they've been taking up properties and building urban infill homes. And they've done that as a demonstration opportunity to showcase what they can do with their students, but also to expose obviously the students to real life work in the field. And we help them with their 10-year plan for their campus. And we basically categorized their campus into anything from mission critical to buildings that they may phase out. But with that, we set up a guideline for how they should build when they build new. And one of the things that found its way into that document was the Passive House standard. And so as the CFO of the college was reviewing all of that, he put two and two together, and he saw, we have these homes that we're doing on a regular basis, and we have this strategy that we want to make better buildings as we move forward. Why don't we bring the two together? And so out came this idea of the passive houses on 24th Street. There is another title for it here, Swift Homes, and you can see the little abbreviation down below. And this is sort of a play on the fact that the site that was chosen is also occupied by chimney swifts. And so part of our green design is that we have to retain, or will retain, living quarters for the birds. So the site that they had was a site that was donated to them that has a 100-year-old greenhouse on it. You can sort of see it in the background. So we coined that phrase from greenhouse to greenhouses. It's big enough for 3 homes. And the greenhouse, in the meanwhile, was reestablished at a different location. This structure here actually was too poor to maintain or transport, so that's being recycled as we speak. But that operation is a different program that the college has a stake in, so that's still alive and well. But it was sort of awkwardly situated because it's in the middle of an urban neighborhood. So on either side and behind, you have typical 40-foot lots and an alleyway. So this was kind of a mismatch, but it had probably been there longer than some of the homes. This is where we're going. We'll keep going back to this here a couple of times. So the programs that we're adopting here for certification, actually we'll probably do 2 of these, not all 3, but I show the 2 Passive House logos just to keep that on a level playing field. So it'll be a certified Passive House. And we're also leveraging a program called Green Star that was born here in Minnesota. Is somewhat of a competitor with LEED, but it's a homegrown, more northern tier program. And we've used that on a couple of projects, and it's a really beautiful program, typically administered by the builder. And it holds the team and the project accountable to the other markers that are important when we talk about sustainability. So with Passive House, we have a very strong energy component. With Green Star, we get all the rest. We get indoor environmental quality, water conservation, how we deal with site and resources and things like that. So we're pooling those two, and we're already knee deep in this process. And that way we can guarantee a very, very high outcome. One of the things, and this is sort of a strategic piece here that we do at INTEP often before we get into a project, is what we call a duty book. So in this particular instance, because we're dealing with a college, so with a group of people, it's not as easy as working with a homeowner. It takes a little bit more definition of a project up front. Where are we actually going? So the first step that we took is to basically write an outline, what is this project all about? And so we went in and we set up some project parameters, square footages, things like that. And then we already pilfered from Passive House. You can see air tightness and some of the building envelope components and energy demands, and basically framed up a document that outlines what is this development going to hold itself accountable to. And in that document, we also started to outline some of the systems that may be leveraged. So it was very helpful to create this guideline up front and agree with all the partners in the mix that that's where we're going, so that at a later date, when you're really focused on the design of the building, you don't have to always revisit, what are we making here? How big is it? And what is it all going to be? So that was already manifested. Another thing, and this is really part of our name as INTEP, Integrated Design and Education Process, we try to bring all the partners and all the information together in one hub as we go through this process. And here we had the added component of having an educational program that was trying to benefit from what we were doing. So we went in and we outlined how the educational program could potentially tap into the design of this house. And so we created on the left side here a column of the steps that we would be taking as the designer of the project. And then on the right-hand side, opportunities for the students and the staff at which point they could interact with the design process. These students are often in two-year programs, so they're not as detailed as maybe a university program. So they're not in a place where they could do some of this work, but they could shadow, and we could check in with them, and they could do little training pieces. And then when we come together for workshops, they could show us what they've done, and we could compare that. And that's actually the process that we used. There were 7 workshops during our design phase. And now that we're entering into the construction phase, we made a similar checklist here for the construction moments at which we could connect. And we're just starting to get into that. You'll see in a minute here how far along the house is. But that's been very successful. And I think the part that's interesting is that a lot of the educators and certainly the leadership is very forward thinking. And while they readily accept a new paradigm like Passive House or Green Star, making it part of their curriculum and really bringing it into their program is still a fair challenge. I think most of us in this industry don't realize how powerful the status quo is and how difficult it is to sort of move beyond and get to the next level and sort of change the way you think about making a building. And so it's very interesting. After each workshop, we would have a roundtable with the educators for each program, and to hear sort of their challenges, how to take what they've normally taught people and now elevate it to this level of construction. And it's something that where they're still learning, and I think there'll be a learning curve all the way through the end of this first home, and likely that will continue through the next couple. There's actually a total of 3 of these houses scheduled here. So this is just kind of a marker of where we are right now here at the end of 2013. And you can see originally there were 4 homes. The city later asked us to keep it to 3. They wanted bigger lots. But essentially we're cycling through a program of design and then construction and workshops and all that in any given year. And the thought is right now that we will do this again twice over after this first one. So let's get into where this thing is. So here's a quick sort of picture of Crosse, and you can see it's sort of on the northern end of town there, and there's kind of a marshy area behind it, which is actually quite nice. There's some trails and pathways through there. So it's close enough to town where it's easy to get anywhere you want, and the campus for both Western and the UW are nearby, but there's some recreational opportunities in there as well. This one here, it's just sort of some photos stitched together, is basically the entire frontage of these 3 lots. So you can still see you saw the greenhouse, and then this is the open lot that we're talking about right now. Here's a quick sort of photo collage of the lot itself. So now we're standing maybe just south of it, and we're panning around. And I mean, this will look very familiar to most of you. It's a typical neighborhood. All existing stuff. And now we're looking at a 66-foot lot, which is a little bit more generous than some urban core properties are, but not completely crazy. Here's the sort of heads-on shot of it, street facade. And so again, this is where we're taking it. And currently we're showing, replicated to the south here, another home that could look the same, but there's some discussion going on about whether we will repeat the same model or make some changes when we move to the next model, and that discussion just started. So when we got into it, the first thing that we did was sort of a site analysis, and this is now a blend of the traditional or typical architectural process, but we also keep an eye on things like views and passive solar heat gains. We had some wildlife here. We're talking about the chimney swifts before. There are some existing obstacles on the property. We had overhead lines. There's a street light that sort of was in the way. And so these are just the things that we sort of ticked off a list as we went through to make sure that we can get a good site design done. And the big piece of that is always the sun, obviously. In the northern tier up here, we can cover over 50% of the heat demand of the building with the sun if we have access to it. And in an urban environment, particularly again in these northern tiers, that can be quite challenging because our winter sun angles are relatively low. So we did a few models where we had different, this is just one of them, but where we laid out these lots in different ways to see over the course of the winter solstice, which is sort of your worst case scenario, how badly they shade each other. And we investigated actually multiple models. We had a staggered approach, which you don't see here, but where we offset the homes, front to back. And that was met with some resistance. In a traditional neighborhood like that, a lot of the people couldn't conceive of starting to stagger homes. And also because these will eventually be sold to the public, they felt that one that had a large front yard and really no backyard may be a home that nobody wants to buy. So pretty quickly we realized, while that's great for the views and the sun, it's not marketable. So we had to step away from that. And the city came back and said, we'd rather have you make 3 66-foot lots than 4 50-foot lots. And that helped us out in the sense that, putting them in line, not staggered, the shading potential from one to the next was so minimal that it actually became possible to make a passive house design on these urban infill lots. And on that note, I'll be blatantly honest. We do quite a few urban infill designs. Not all of them always move forward and get executed. And I can tell you that in our tier up here, given our climate and the way that the sun angles work, urban infill lots that are 40-foot narrow and in a neighborhood that is normally built up almost eliminate the chance to make a passive house. So we're clearly in a place on Earth here where passive house has its limitations. I think Wolfgang Feist would probably like to disagree with me as the founder of Passive House because he feels strongly that you can do it anywhere. But what we're finding in our models is that if the lot is narrow and your neighbor is right there, and for most of the winter, the neighbor is shading you almost entirely, without that solar heat gain portion, it's virtually impossible. It doesn't matter how well you insulate the home, you're missing the other component, the free heat. And the reason why Passive House works in our climate zone is because we have a tremendous amount of free heat. And this comes out of the tradition of the Central European climate, where, over any given year, the Germans are perfectly happy if their heat gains and losses through the windows balance each other out. But in our tier up here, we can actually pull more sun in than we have heat loss through the windows. And that's what makes Passive House possible up here. So again, as a sort of a result of that, if you are in a location where either the orientation of the building or what's around it take away the passive solar heat gains, it gets really difficult. And we are making some of these homes. We're working on one right now, and we're essentially letting it drop back from the passive house parameters. We would design it the same way, build it the same way, but have to live with the fact that without the free heat, it's not going to perform at the same level. And that's just the reality of where we are. And that doesn't make it a bad building, by the way, either. All right, so sticking with the site design, I'll just run through this quickly. We're working with students. There's some landscape students there. So we made a land use plan. So we're looking at, how do we drain water? We looked at how do we deal with it responsibly. So we had a series of rain gardens we devised. We figured out there's going to be a front yard. We have entry situations, both from the front and the rear. We decided we were going to plant some new trees on the side that we can use for shading when we want it. We have, because of the width of the lot, a still very meaningful side yard, which is nice in an urban setting to have. We have a backyard, and we're going to do some modest food production here on each one of these lots. Then we have an area that's designated for storage and some privacy screening with greenery. And then last but not least, we have an apron and a garage, and we kept that very minimal. The idea being that we want as much of that site put to use for the enjoyment of the people living there, and use as little of it as we can for driving around and parking stuff on. So here's the first schematic. And one of the things that sort of transpired from this is there was an exercise that the students did that suggested, let's just fuse all three properties. Here's all three of them in a row, and make a courtyard or something like that. And one of the things that we found is that that could become quite difficult. If you, let's say we shared some functions here, what happens if these homes were to be sold individually at some point? Do the people always get along? Does that put them in a condo association? And for 3 units, is that worth it? And ultimately, with the owner, it was decided that they want what they call lot independence. They want to make sure that each property functions completely independent on its own. There were some early thoughts about having a shared energy pod, one heating system for all three. And while all these things are exciting, again, it was decided that we want these ones to stand alone. And so basically the design that we made means that they each can have all these components and be sold off as that, and they don't depend on each other. The initial concept that we had went back to something that TE Studio, my residential company here, worked on a number of years back, called the synergy concept. It was looking at sort of an affordable urban infill model. And we just sort of stuck with some of the key parameters that we set forth for that. If you want to do something cost effectively, you better keep it simple. So we wanted to make sure we had a simple and basic building envelope. And that's why we end up with a very basic shape here. We want to make sure our structural components are not outrageous. So we had a very basic sort of structural setup. And then last but not least, we want to have some clearly defined vertical elements. This is not the exact floor plan, but just sort of a graphic to show in red here, for instance, a wet wall that is vertical throughout the whole house for all the mechanicals to run, or a stair that is in a defined location. So we wanted to make sure that we keep these things pretty straightforward. And then obviously we went through a schematic design exercise. This was one of the intermediate steps here. There's a couple of different floor plan iterations that we went through. And one of the things that we found is that on that second floor of the structure, we have some flexibility. The way that it's built, it could have a few bedrooms, or it could have a lot of bedrooms. It could even have an opening to the story below. So we made a design structurally and from a mechanical systems perspective that allows for flexibility on the second floor. And that was important because we don't know who's going to own the building and live there. And so now we have a design that 2 people could happily live in and maybe live and work. But there's also an opportunity for 5 bedrooms, and it's all happening on the same footprint. The other thing was that with the basic structure that we devised, the hats or the roof lines really became interchangeable. So with the same model, it was possible to make different architectural and design expressions here, and really for almost the same cost, we can generate something that looks very differently. And this was an image that was generated to illustrate that to the client. This is a shot from the backyard. So this is the current design that's being built now. So this is sort of the southwest corner. So again, that was our end result, and I'll run you through the plans real quick. This is the site plan. This goes right back to the land use plan that I showed you before. It's just basically a well-developed version of that. So we have still all the parameters: the side yard, the front yard, the garden, the rain gardens and fruit trees, and all those things here in place. And that again is replicable across all 3 properties. So that takes sustainability, to a very high level. It has very little to do with Passive House, actually. It's just good practice, to maintain the lot or create a lot, I should say, that provides many assets, shaded spaces, opportunity to grow food, and deal with stormwater responsibly. Here we get into the footprint now. That's the first floor plan. So it's an open floor plan, as we would call it as architects. So you come in the front door and you essentially have an open living, dining, and kitchen area. A lot of people prefer to live this way these days. They don't want compartments so much anymore. They appreciate the open space and the flexibility that comes with it. We have a stair on the north side in the middle, and really all the utilitarian spaces and rooms here on that level are oriented to the north, as we want to avoid as many windows as we can on the north side, because in a cold climate, those are net energy losers for us. You can see the windows on the south side are a little bit bigger. And in this particular case, there's actually a deck off the south side, and we have these French doors that open up. And that's a theme that continues up to the second floor. We also have a mudroom. Again, in a cold climate, our winters are long. We want to make sure that when you come in from the rear, from the garage in this case, or the backyard, that you have an area to clean up, to drop your jacket and shoes off. And that's actually where we have the laundry here for this house as well. And it acts as overflow storage for the kitchen. There's a bathroom on this floor and a bedroom. And the reason why we did that is we wanted to make sure that people can age in place here. So everything that you need to live is essentially there on this first floor. And this guest/TV bedroom that we're showing there could also be opened up to the living room. The way that it's being framed, it allows for that wall between it and the living room to disappear. So if people don't desire a bedroom on this floor, they can have the bathroom be a powder room and have a much larger living space. On the second floor, this is the arrangement that's going to be built. I mentioned earlier there's a potential for more flexibility here, but we essentially have a 3-bedroom, 2-bathroom setup with a master suite with a very generous closet and a generous bathroom, and then 2 smaller bedrooms with a full bath. The master closet could also be turned into an additional bedroom, and then that master bath be shared. So you can see how we could very easily get from the 3 bedrooms to 4 bedrooms on this floor. And then we have an additional one on the main level. That's the 5-bedroom option that I talked about. And then the basement initially is going to be unfinished. There is a provision for yet another bedroom potential on that level. We have a small mechanical space. There'll be a bathroom roughed in. So there's lots of room to grow into down here, or room for activities. And the basement's gonna have full ceiling height so that it can serve as overflow living space. So by no means is this a small shoebox. There's about 2,600 feet, useful feet on these 3 stories, and we think it's a very flexible program. All right, assemblies. So for those of you who are particularly interested in Passive House, this is the part where it gets exciting for you. So we investigated multiple ways to make this. There's always more than one way to make it, and there's probably more than we have here. But we also want to do it cost effectively, and we want to do it in a way that the people we work with, in this case, the construction company here, feels like they can do a good job on executing it. So we offered them 3 ways, for instance, to make the above grade walls. We looked at a double stud wall. We looked at one that's framed with I-joists. And then we looked at this last one, which is a combination, a stud wall with I-joists. And I apologize, the 2x6s in that wall don't show up on the right-hand side there. They must have been hidden. So in any case, you're looking at 3 very different wall setups that deliver the same performance. So from an R value perspective or air tightness perspective, they can all deliver the same end result. What they have in common is it's all wood construction, but still between them, there's subtle differences. The contractor looked at that and evaluated that and ultimately picked the one on the right-hand side, the stud wall with the I-joist. They felt that that was the one that they could do most economically, and also the one where they felt they could execute the quality the best. This is also where our energy model comes in and helps us out. This is sort of a pie chart that we grabbed off of the Passive House planning package. This one here breaks down the heat loss by component for the building. And this is something that is really helpful for the designer, but also the construction company. And when talking with clients, when we're looking at where can we trim the building, or where do we put our resources to make this the best building that we can. And in this particular case, you can see, the above grade walls here. The windows are still the biggest loser, quote unquote, for this building. And this is after the fine tuning of the building. And that's pretty common. This would look different if you built in a different climate zone. But for our northern tier, this is what we would expect. So we're leveraging very high-end window technology. But even with that, the windows are the weakest link in the building envelope. However, having said that, they also account for the solar heat gains, and we'll get to that in a minute, but that's important. So we practice performance-based design. We're trying to get to a certain level of energy performance, so we can use this model here to help us tweak our design. And in this particular case, it may be the difference between a 12-inch I-joist and a 14-inch I-joist on the exterior of the building. And we can see how does that shift the balance. We can also see if we've maxed out components. So if we go through our model and we start to add more insulation to the basement, or to the front door, which only accounts for 2% of the heat loss here. It's one of those things where you would have to do a lot there to try to affect the whole pie, if you want. So again, we use this tool actively through value engineering and in our design to make smart decisions about how far to take which component. This is not all that important, but there was a preliminary pricing exercise, obviously, and so we brought something to that, and the contractor brought something to that, and this was very helpful because one of the things you have to understand is in North America we don't have a tremendous amount of these passive houses just yet, and so the cost varies greatly depending on where you go in the country. So while we have a pretty good understanding from past projects where costs are, you still have to price these projects locally. And that's probably true for any project because the building industry may be different from one place to the next. And so that's something that we did here. And we also found some delta T's in the pricing. I can't show you that because it's confidential, but there are some categories where we found the contractor is way cheaper or way more expensive than we would have anticipated. And that then led to an exercise of talking about these systems or components to try to understand why is that. And sometimes and many times actually, it's just a basic misunderstanding where they maybe misinterpreted a system because it's just different enough from how they normally work. And then we can find those errors and make them right. And so here's kind of the process of value engineering in a nutshell. So you see Stefan and I representing Intep architecture, and then Fowler and Hammer as our GC in the middle. But you can see us, going through this exercise. So we're looking at, takeoffs. We're looking at how effective a component is to the design, and we're looking at how much it costs, and then we're tweaking the design, in this process as a team. Again, integrated planning or integrated design. We're doing that together. We're not just confronting them with stuff and waiting for things to come back. These are actually joint exercises. Yeah, so then I'll tell you a little bit more about the performance-based design process. And this is important. This is where we are building, for those probably online who are in a completely different climate zone. That picture I took in May of this year. Those of you here local will remember that dreadful day. So it's important to understand where we are, and that really has an impact on how we make these buildings. And again, we go through this cycle then of making our building model, our building design, and energy modeling it at the same time, and they inform each other. So we tweak our design or we tweak our energy model, and the information we gain from either one is fed back into the other. And so we jump through this cycle of optimizing the building. And we're always with the Passive House performance parameters as a target, obviously, in the background. But that's really how we adjust and fine-tune the design to the specifics here. As far as the building envelope goes, we are in a cold climate. So conventional buildings built to Minnesota code are probably that jean jacket there. They're full of holes, they leak, and they have a fairly minimal R value. Anybody who's been to Minnesota in the winter or western Wisconsin will know that this is going to work much better. So here we have a continuous building envelope that we need to make, and it's likely going to have much higher R value, and it's also going to be tight. You don't want the wind blowing through it. That sort of negates the whole idea of having high insulation value in the first place. This is a screenshot from the Passive House Planning Package energy model. And so here you can see the U values. So we're literally modeling then each line item of an assembly. This here is the I-joist wall that I showed you earlier. And we're putting that in. And at the end of the day, it spits out the U value. I have to apologize, this is metric, but I grew up in Germany, so that's how my numbers look. This translates to, I don't know, an R60 or 55 or something, and I guess. But that's how we input the whole system into the Passive House Planning Package. It's an Excel-based system for those of you who don't know. And from there, it informs the entire building model. So then in this particular case, we're comparing the cold climate standard construction, R19, and this is what we ended up with. Again, the 2x6s went missing, but the rest of it is there. So something between R55 and R65 is what's needed here to make this particular structure. Now, while adding all that insulation to the building, it's really important to also understand what happens with moisture. And that's one of the biggest sort of fears that a lot of people have. You know, you make a building tight and you add insulation, isn't it all going to rot? Well, if you don't do it right, it certainly will. We want to make sure to do it right. So we also run a basic hygrothermal analysis. We use a sort of back of the hand version that comes out of what we learned in physics class in Germany. But we made a little Excel spreadsheet that spits out a little diagram here. And as long as those two lines don't really touch or intersect each other, that tells us that we don't have a dew point in a place where it could wreak havoc. And so we try to make assemblies where we have enough of a distance we know they won't fail. There are other software models out there that, like Woofy, for instance, that people could leverage to do a dynamic model and find out, is this assembly safe over 10 years with the onslaught of our climate. I'll tell you a little bit about how this thing will be built then. You can see sort of a section cut through the structure here on the left. And then again, on the right-hand side, a screenshot from the energy model where all these inputs are reflected. The average building envelope, if you take windows and everything that we have here, is insulated to an R36, which is actually not outrageous. If you compare it to the R19 nominal value for maybe the traditional code building, although that doesn't account for thermal bridges, and this does. So here we have our below grade connection. We decided to forego the traditional footings that are buried in the ground and put the footings right into the basement slab, and then set the entire building down on a packet of foam and essentially clad it or wrap it with more foam up the side walls. So the entire basement is essentially wrapped like a cooler, or in this case, we want to keep it warm, obviously, with EPS foam panel insulation. That's something that works beautifully structurally, and it can easily be executed in the field, and I'll show you some pictures of that in a moment, what that looks like. In areas where we didn't need the slab to be fat for load-bearing purposes, we substituted with sand fill. So we're being material efficient here, and that sand fill was actually the excavation on site because they had sandy soils. We just recycled it right into this particular system. The concrete itself, because we're going with a Green Star program, has over 40% fly ash content, so we're reducing the embodied energy footprint of our assemblies as we're going through this. Again, we're adding to the passive house here with a different model, but that helps keep the embodied energy footprint low. Our below grade assemblies are insulated to about an R39 continuously, no thermal bridges. Here's the transition then from the basement stem wall to the above grade construction. You can see the concrete wall coming up. It's completely wrapped, again, in a foam panel insulation. The interior floor system hung from that. And then we have a structural 2x6 wall with exterior OSB sheathing. So if you strip out the I-joist that is hanging from that, we're essentially building a completely conventional building at this moment in time. And that helps the builder out because that's a paradigm that they know. That OSB layer is our air tightness layer, and it's also our vapor management layer. So that sheathing will be taped, and because we're doing it on the exterior, we can see that very well then in the field later that they did a good job taping all the seams. After that, I-joists are hung from the exterior of the building. They're later packed with cellulose insulation. All of these cavities are, and then we have our ventilated siding system on the exterior. So very basic construction. And as we get to the top, there's of course an intermediate floor that doesn't really show anything exciting, so I'm giving you the top here. We essentially have a truss system over the top with an energy heel. That just means that the truss is tall at the edges of the home, so that we have roughly the same amount of insulation wrapping all the way around the corner. And then up above is an attic that's ventilated. So again, just a bunch of good common practices, more of it, in that our insulation blanket up here is about 2 feet thick. It'll later settle down to about 20 inches over time. And that roof has an R value of 83. I think the wall one was shown on there, 58. So that gives you an idea. So there's a slight progression of R value And the reason why we do that is, particularly in the roof, it's very easy to get a very high R value into the roof when you loose fill insulation up there. So that's an easy and inexpensive place to pick up good R value. In the walls, we're pretty much maxing out with this type of construction. 2x6 and a 16, I'm sorry, this is a 14-inch I-joist, so we have a little bit of room, but at 16 we would max out. They don't make them any bigger unless you custom order them, and that gets expensive. So we try to work with product that's readily available, and for the La Crosse climate, that works out fine. Right now we're working on a house on Beaver Island in Lake Michigan, and we have a similar system with 16-inch I-joist, and again, that's about maxed out then for this type of construction. Air tightness, very important. So a couple of comparisons here. I've tested a lot of buildings, and existing buildings are all over the place, but a really good one, newly built, is maybe at 1.5. I'm sure there are builders out there who can beat that, but on average here in our climate area, that's what we see. A lot of them will be around 3.0. And used buildings, I've tested anything from 5 on up. I've tested some that didn't pressurize at all. So in comparison with that, with Passive House, we need to hold ourselves accountable to the 0.6, so quite a bit tighter, which means diligence and good detailing, and caulk and tape and products that lend themselves to making it airtight. Our target for the La Crosse house is actually 0.4. We always aim a little higher just to keep everybody alert. And while the differences between those two numbers may mean 20 or 30 CFM in the field, which isn't much, I think it just gets everybody's attention up. And we want to send a message to the builder that, we don't want to sort of run this project at the bottom level. We want to aim higher. And that also gives us a little bit of wiggle room should there be any problems. Okay, so now for the heating portion, again, another shot, taken in May up here. So this is where we get our free heat, right? Windows. I'm giving you a comparison again. So the conventional American window that you'll see, and interestingly enough, even though we have 7 climate zones, the conventional North American window is the same wherever you go. Has a U value of about 0.3 thereabouts and a solar heat gain coefficient of about 30%. Air tightness will be low to high. So that's kind of the baseline. If you want to make a passive house in a cold climate like this, you need to up the game quite a bit. And unfortunately, at this point, there's still not a North American manufacturer who's embraced that. There are some who are moving in that direction, but not for our cold climate zones up here. So this is mostly European product. You can see for those here in the room, we have a couple in walls here. You can play with them later. But you can see the enhancement here for the U value and the solar heat gain coefficient. These are just on a completely different playing field. And this product is what makes Passive House happen in a northern climate. And we actually install these also in buildings that don't quite get to the Passive House level. And if you remember that pie chart I showed you, windows account for the biggest heat loss in virtually any structure. So, I would even make a case that in a code compliant building, you can yield something by going with a good window. They may just not fit because they're maybe wider than the wall that they need to go into. So the windows become heaters. Here's a quick balance from the Passive House energy model. And you can see over the course of an average year, we have 3,600 some kilowatt hours in heat loss through the windows and 4,200 kilowatt hours in heat gains. So we can actually pick up free heat. And that's what I was talking about before. That's helping us here make a Passive House in the cold tier. More gains than losses. That's what I was trying to get at. And then, the overall R value for the window is quite high compared to conventional windows. In this particular case, in Imperial, it's about a 0.15. And that's already accounting for the thermal bridges that exist around the installation and the heat loss through the frame. So at that, it's easily 3 times better than conventional stuff that you see done. So now we have a really good building envelope. We need a mechanical response. Something that can make up the rest, because a passive house, just like any other structure, still has some heat demand and maybe even some cooling. So in the energy model, we also receive an output for that. So in this particular case, we have a heat load of about 3.4 kW. and or 14 watts per square meter. And that translates to 6.4 kBTU an hour, and that's about a 90% reduction over conventional construction. And it may even be more. Most homes, quite frankly, in our area are built with often an 80 kBTU or 100 kBTU heating plant. So you can see we're at 6.42, quite a bit less. The PHPP also spits out a nice graph that shows us what our heating season actually is. You'll see the gray bars at the bottom here tell us that sometime maybe in late October, early November, the thing has to kick in, and then essentially it runs through March. I can tell you from two buildings that we have up and running here locally, it can actually be shorter than that. And that has a little bit to do with what do the homeowners do. Again, bake bread and do some laundry on a November day may just do the trick. So from that angle, the Passive House in the Woods, which was shown earlier, the heating season in there is usually only 3 months. So the biggest losers, we talked about it, are still the windows and also exterior walls. The biggest winners are the passive solar and internal heat gains. So again, they contribute a lot of the free heat input here and then work in concert with our mechanical system. And I'll get to that in a second, how we heat it. I want to give you the cooling load real quick too. For this house here, it's basically a half a ton of cooling. And there's the graph with the cooling load over the course of the year. That half a ton happens pretty much in July. There's just a little bit in August. And we decided to install a system that can do both. Now, this is something that I think has a lot of potential for the residential scale passive house. The unit in the center at the top there is what's called a slim duct heat pump. So it's essentially a air-to-air heat pump system that can accept a minimal amount of duct work. So that unit gets buried in the ceiling and can receive basically a trunk line and some branch lines to supply the house with heating, and in this case, actually cooling and dehumidification. The unit is wired up and plumbed up to one outdoor unit. We have one of these on the first and second floors, so there's two of them in the house, one exterior unit. They have a fully programmable thermostat, and on the upper left-hand corner, you can see an electric resistance heating coil. Why do we have that? Simply because our lowest design temperature of the year exceeds the capacity at which the outdoor compressor is still allowed to run for this kind of a system. So we can get down to, I want to say, about 13F or maybe a little lower, but then at some point there is a handover to the electric resistance system. So ultimately on the coldest days of the year, there'll be some electric resistance input. During all the other times, there'll be a coefficient of productivity that comes out of using a heat pump. In the summer, obviously, it's just cooling, straight up cooling. We also have a ventilation system, and that's really at the core of Passive House, right? The mechanical system revolves around it. And in this particular project, yeah, I don't know who came up with these cool flavors. I want some of those cans. Actually, the last one, I don't know if you saw that on the right, says, no, the second to last one, horse flavor. That's probably more acquired taste. Although I grew up in horse country, I can appreciate that. So heat recovery ventilator with home run distribution system, that's been our weapon of choice for the ventilation delivery on all of our projects. As much as many mechanical inspectors across the country try to stop this from happening, these systems are phenomenal. They're very simple, easy to maintain, easy to put in, very cost effective. So at the heart of it, on the left, we have the heat recovery ventilator. In this particular case, if anybody cares, it's a Zender Paul Novus 300 machine. And then the big pipes that come to and go to the outside in the middle are something called ISO duct or Comfo pipe, I think Zender calls it. It's insulation and duct in one. So you're not running duct and then trying to insulate it. It's actually made from EPS foam. So it just plugs into each other. It's a basic system and it's very bulletproof. The pipes that you see on the right-hand side are flexible pipes made from plastic, and they're essentially like PEX tubing for your plumbing, but in this case, you blow air through them, and they connect from a central manifold to these outlets you see on the upper right-hand corner, and then the little white thing you see next to it is the grate or the diffuser, I'm sorry, that would plug into the bottom of the ceiling outlet and squeeze the air into a space or suck it back out. So in a nutshell, that's what that is. I had a little video here. I can just sort of let that run in the background. These are the tubes. You can see I'm going to open this up here, and they have that ribbing on the outside, but they're smooth on the inside. So they don't provide any resistance to the air going through it. They can be installed in concrete. They can be embedded in it. So in wood construction, they basically just get suspended in a ceiling or run in chases. So that's a pretty basic setup. We'll let the video catch up with me here. I think there's another sequence here where we're showing you how it all plugs in together. There's a little rubber O-ring that gets inlaid into the grooves. And with that in it, it can plug into the receiving end of either the manifold or the diffuser box in the ceiling. This piece here is a connector. So if you had a pipe that wasn't long enough, you could fuse two together by clicking them into this connector. There's the diffuser box in the ceiling. And you can see it has two inlets. This is all made from plastic. The Zender one I showed you was made from metal, but it's the same concept. The opening on the bottom that's currently concealed is where the diffuser will go later. You basically run it through, you plug it in, and you walk away. I mean, it's as basic as that, and you got ventilation to and from a space. This is a manifold by a company called Inno Products. It's also made from plastic. The end caps would be cut open and the hoses plugged into it, and the big hole in the top gets knocked out and connected to the unit. So again, you can see these are very basic components. We have them here in the office. If you're local here, you can play with that later. But that's essentially how that system is being put together. Yep. Okay, we'll skip over that. And then we need to heat hot water. So by the time we're done heating the house and insulating the house to the level that we did, we're finding that the bigger component here is really hot water. It's rising to the top now as a consumer of energy. And on the La Crosse house, we decided we're going to preheat this with a solar thermal heating system. There'll be 2 panels on the roof of the house, about 4 by 10 feet in size. And they exchange a glycol mixture with a heat exchanger in a storage tank in the basement. And that storage tank on many days will be sufficiently hot just from the roof. The system is geared to provide about 85% of the hot water needs for a family of 5 in the home. So if there were fewer people in there, this could go up to 100%. And it is a so-called drain back system. So when the tank is satisfied and there's still sun up, we don't need it anymore. The panels simply empty themselves of the heat exchanger liquid and go idle. And if there's another call for heat, the panels receive the liquid back again, come online, and start providing hot heat for the storage tank. And then attached to the storage tank is an on-demand electric backup booster. So if there's ever not enough, or the owners decide they want to take a dozen showers one after the next, there's essentially endless heat coming through the system because we have an on-demand water heater that can heat essentially city water temperature to full temperature. So or anything in between that and what the tank has. So in the system, as long as we have electricity, we'll never run out of hot water. And that's a great way to avoid some of the primary energy. Once more, again, 85% is being delivered here through the sun. Here's a little thing that we do for some projects, not always, but where we can. It's something we call an energy balance sheet. So we break out where do these energies actually go? What do we have coming in and what do we have going out? And what are we predicting as consumption for an average year? And so we're breaking it out into the green is basically what we're getting and the red is what we're spending. It's kind of like money here. So we got solar heat gains coming in. We got internal heat gains coming in. We have some active heating with our heat pump and some backup heating with electric resistance. We have some backup heating on the domestic hot water and some free heat coming off the roof. And then we have the plug loads, which if you were following this carefully, you'll see they are amazingly large compared to everything else. And what is plug loads? Well, that's the people living in it. That's lights, that's iPods, that's gadgetry, appliances, and the lot. We have some auxiliary energy. Those are components that are needed, like the ventilator, mechanical equipment. And then we have a very modest cooling component here. And we're estimating right now that a family of 5 will need about 11,250 kilowatt hours of electricity a year to run this. This is single fuel, so this is for everything. If we go to 2 occupants, it'll drop down to about 7,500, and a huge part of it is in the plug loads. And we are accounting for a North American lifestyle here, which is one thing where the Passive House planning package, given that it's coming from Germany, is just not very good. Here's a comparison. Of course, this means nothing if you don't see this in contrast. So the average Wisconsin home blows through 30,500 kilowatt hours of energy in a year. So if a family of 5 were living here at 11,000, we're down 2/3 on energy footprint. In Minnesota, it's actually worse. And you can see if there are only 2 people in there, it gets better and better. So as it stacks up and lays out, our energy footprint is really, really low, which sort of segues into the conversation of, well, what if we want to get to net zero? Or as in this case, what if the owner, the technical college, has a few solar panels floating around they don't know what to do with? Then we get into an exercise like this here, trying to figure out, what sort of offset we can provide. So we made a little worksheet, and this is also going now beyond just simple living. If you scan down the third table, you'll see that it says vehicle right there. So we're living in the 21st century, and we're recognizing that vehicle and transportation is moving into the realm of electricity. So it's no longer enough for us as architects, as we're designing buildings that are surely going to be around for more than 5 years, to make that part of the design. So this building and the garage are actually connected so that there will be vehicle charging points in the garage that connect back to the house. And we've designed that in a way where you can actually connect fast chargers to it. So not just that 16-hour trickle charge, but we're putting a fat pipe that allows for fast charging. But with that, as we're looking at renewables and offsetting, we started to make an equation. So we had to dig in and find out what is the efficiency of electric vehicles, and we found that they can go so many miles on a kilowatt hour of electricity on average. And we actually also got into the CO2 footprints, but I'll spare you that because there's a lot of geekery when you get into that. But what we're finding is we can provide certain offsets with a certain size system. Now, from the college, we got basically a 10 kW PV system that they have, and we know that has a certain output in any given year. And so we broke out, just to kind of keep it simple, 3 line items here to transfer. What does that mean? With that system, they can become net zero for 3 people in the house and 1 vehicle, or 6 people in the house, or 2 people and 2 vehicles. So you can spin it any which way you want. There's more scenarios thinkable, but that was the discussion that we had. It was also part of a workshop, just to put it in perspective. And maybe on a personal note, as net zero becomes such a hip word that is really playing a great role in our residential building industry these days, I think it's important for people to realize that that is not a very easy target to get to, and you shouldn't take that too lightly. You can see 10 kW is probably twice the size of your average residential PV system, and yet the offset it provides, even with a house that's incredibly high performing, is just what you see there. So we're in a cold climate. We have a larger energy footprint here than people elsewhere in the country, but that's about as far as we can take it reasonably. All right, so then at the end of it, hopefully there's the verification page and the Passive House Energy Model and the Passive House certification with the Passive House Institute. We produced an energy model that had the little yes, I don't know if you can even read it at the bottom, but the verification tool tells us, yes, this is a passive house. And in working with the Passive House Institute, we've worked through the various questions and answers on that, and we now have an agreed model that is a passive house, and as of 2 days ago, I think they're listing it on their website as one. Construction, and this is where I close. So the building broke ground, I don't know, some 3 weeks ago maybe. So we're not terribly far along, but I'll give you what we have, because I'm sure you'd love to see what that looks like. We'll start with the site and the site preparation here. Again, there are some Green Star components here, so we made sure to keep the excavation on site. We're hoping to recycle a lot of that. There's a lot of erosion control and things that went in just to make sure that we're environmentally sensitive all the way around. There's recycling, there's waste mitigation, we make material piles at the end of every day so that stuff gets reused first before it gets thrown away, things like that. The actual digging a hole, though, is still just work and not very sexy. One thing that's important in many places in North America is radon. I just want to say something about that as well. In Minnesota, it's actually code now that we have to put in a passive ventilation system. And just because we're across the border here doesn't mean that the exposure changes. So while Wisconsin didn't require that, we're doing it anyways. So we're putting in a perimeter drain and passive radon vent. So trenches dug and filled with some gravel, and essentially a sort of a wrapped pipe installed to a sump system. And you can see the sump basket there on the right-hand side. So we have all the components in place for a passive ventilation from under the slab. And if the radon exposure should be high, this system could be made active with the help of a fan. And these things, I think it's also important to note, we're trying to avoid, obviously, energy, and running a fan all day and all night wouldn't be great. But people and life safety always comes first. So these systems make a lot of sense to have. And this is something that you can't very easily dig in after the fact, especially if you see how we do our basements here in a minute. So you can see the plumbing was stubbed up first, all the supply lines, waste lines coming up. You can see that perimeter drain and somewhere that sump basket sticking out. A little bit unusual for the contractor because more often than not, they don't go about it in the same phasing that we're doing here, just because they do perimeter footings and then they work inside of those. So our staging and phasing is a little bit upset because of the system that we like, with all insulation first and then build up from there. But that's all pretty standard stuff. And then at the end of the day, everything's stubbed up and coming out. And you can already see where these pipes are sticking out of the ground here is on the left and right hand side of the stairs. So we're leveraging that as a vertical core through the building. This was the excavation for the sump basket. So if you really want to get into continuous insulation levels and you care, that means even if you have a sump basket sticking down into the ground, you'd better dig a nice hole, and then you build a little foam box, and then you stick the sump basket into the foam box. Okay, does that really make a difference for the house? We did not calculate the heat loss through the sump basket, and as you can see, that's only a couple inches of foam. But we felt in a demonstration project, we just wanted to make a point that this is part of the insulated building envelope, so it should be taken care of. And so we did. And so it's insulated. So then they started to smooth it out, and the foam panels go in. These are, from memory, I think these are 10-inch or 9-inch. I think they're 9-inch. I apologize. I do too many projects simultaneously to remember all the inches, but I think that was 9. And they basically put them in a running bond. This is also, I think, one of the, maybe the first project where we procured the product at the final thickness so that there isn't layering, because that adds a lot of labor, and there's potential failure points with that. So they did a really good job of sourcing this, and we finally have a good supply chain for this stuff. EPS, because EPS is highly recyclable, it may or may not have recycled content already. And out of all the foams, this has the lowest embodied energy footprint, so it's the most benign product. Also, the blowing agents and everything involved in this makes it the most benign foam. So we're working around all the protrusions. They're all sealed up. We need a continuous envelope, so we need to, not just for air tightness, but also for the thermal integrity, insulate around it. Technically, each one of those pipes is a thermal bridge, but those systems we have to have. We can't negate that. So you can see the whole thing coming together. These are kind of the tools of the trade for the next step. You can see a lot of tape there and maybe some sealant and some tarp. So the next step is we're putting an airtight layer in over the top of that, which in this case is also the vapor retardation and also the weather barrier if you want. So this is really the demarcation line between in and out. It's 2 layers of poly staggered joints, fully taped and sealed. There we go. Everything's sealed up to the sump basket. And then you can see the sand I was talking about earlier. So we only need the slab to be so thick in certain places for the footing. So in the other spaces, we were able to just use what we had on site and infill. And when I say we, I mean all these fabulous people who actually do the work. My hands are clean. And this is how it's coming together. Rebar going in. Now we're back into sort of standard territory of concrete construction. Rebar, remesh going in, and then ultimately a slab being poured. Just next step here, and there it's being troweled. So at the end of the day, what we're looking at is just a slab with structural properties on top of a bed of foam. And then from there, we continue with the concrete walls. So there's just formwork being placed all the way around, rebar placed in that, and then that's being insulated. And unfortunately, that is as far as I can take you because that's as far as they are as of yesterday. So the formwork for the basement coming off, and you can see it's rising out of the ground. So it is happening. This is number 1 of 3 as we see it today. That's the Crosse Passive House. This is what it'll look like when it's done from the street. Here's another shot again from the backyard. And with that, I close and leave you with some resources here. And thank you for your time. Let's do some questions. First things first here, we stole images from, no, we didn't steal. We asked these people to kindly lend us images, so thank you there. That's us, that's our resource here. But what I want to bring back, I'll leave this up as we talk here, just so you can take notes if you want to. I'll watch for online questions, but I'll take anything here. There's nothing online yet, so please go ahead. Yeah.
The plastic over the floor, were each layer, were they sealed with the penetrations individually?
Yeah, the question is if the plastic layers, each layer was sealed individually at the penetrations, and the answer is yes. And again, if we worked with a builder regularly on some of these items and they understood the importance of the integrity of that layer, I think it might be reasonable to go down to a single ply and not jump through these hoops. But when you're doing it for the first time, it helps to have some belt and suspenders approaches in the mix. And I think they appreciate it as well because it's an insurance policy for them that they'll end up at the right airtightness level and all that. We've done it this way now on a number of projects. I know in commercial construction, there's also products that do the same job. There are rubber membranes you can buy and rubber boots. They tend to be kind of spendy. You know, if you're building a high rise, that's one thing on a residential home. So, and at the end of the day, they actually bought a roll of plastic that was wider than the width of the home. So they really didn't have any joints. They just laid it over the top twice, cut a few slots as you saw and taped it. So, you know, yeah. So very basic in that sense. But yeah, we do the diligence. You could see they photographed it by, you know, pulling it apart to show us that, yeah, that's really 2 layers. Yeah. Jay.
When you did your solar studies, did you ever explore windows on the roof? You know, you're talking about, you know, shading and solar heating.
Right. Yeah. Sure. So the question was, did we ever look at windows in the roof when we're looking at the urban shading that's happening? And I haven't done that specifically on a design, but it is something that we've conceptually tossed around. So it's something that if or when that comes up the next time, I think there's an opportunity to investigate that. If you do basically skylight is maybe the wrong word, some sort of a transom window area on the roof that picks up and funnels light and heat down in a way that there's maybe a potential to become better. I mean, so much of it really has to do with what does your next door neighbor or that obstruction look like. And if that's a half story taller than you are, even in, you know, then it doesn't matter if you put it up on the roof, it just won't work, period. Again, the low sun angles here are just brutal. And so I think as a concept, it's worth looking at in the right condition, but I know I've also worked on projects where that wouldn't have made any difference. Yeah. Yes?
Are you always using HRV in this climate?
Yep. That's a great question. So the question was, do we always use an HRV or do we use ERV? And, you know, we have sort of a rule of thumb for that. We figure large house, few people, ERV, small house, lots of people, HRV. The reason being that with ERV, you end up in the winter, you end up retaining more moisture in the home. And in the summer, if you're actively cooling, you actually have a potential to reject some. So energetically speaking, there's some good argument to be made for an ERV. But on the flip side, if you have a small home with lots of people in it and lots of moisture being generated, you may expose the building to quite a bit of moisture on the inside, and you can't effectively expel it because that's not what that system is designed to do. And quite frankly, I think the best systems, in my opinions, are the ones that have a slotted core, where you can, for $500, you can buy both, and then you can swap them and basically, do that based on your comfort and the relative humidity levels you have inside. But in this particular case here, it's an HRV system because there is an expectation that there's going to be a good density of people for the volume inside the house. The other thing that I will say to that, and I'm living with an ERV in my own home, is that ERVs, because of the way that they work internally, they tend to they can basically retransmit odors back into the house, simply because they typically have an enthalpy wheel. And while the airstream isn't really supposed to mix, and I don't think it really does, the medium that's used in that wheel to transfer the moisture from incoming to outgoing can effectively absorb for a brief moment in time, particles that make up odors, and they get pushed back into the house. From my own experience, I can tell you the highlights are red meat and onions. So it's really, and the question is that all bad? My wife, for instance, appreciates when we have a good meal that some of that smell stays in the house. So you can look at that both ways. I have some clients, though, for whom that would be completely unacceptable. And so we make that decision on an individual basis based on these parameters. Let me just look here real quick. There's an online question from Patrick. With the basement being unfinished at the time of construction, did you discount the entire basement square footage in the PHPP area calculations? The short answer is no, we did not. It's all in there as if it were fully built out. And to be honest with you, Patrick, there is a fair chance that it will be fully built out. It was basically designed that way to allow the owner to pull back a little if they should for budget reasons. But my feeling is that it's going to be a completely finished product by the time that it's done. So it's not really an issue here. And I'm not sure that I would have a guilty conscience running it this way through the certification. And I believe that conversation was had with the PHI in this instance and was found to be acceptable. But your results may vary depending on who you're working with for certification on something like this. That's the only question I got here. Yeah, let's start here.
Why poured concrete versus ICF? What was the advantages?
Sure. Question was why poured concrete over ICF? It's not necessarily a simple decision. Again, in an integrated design approach, we're working with our builder. We're trying to understand what can you do well. In this case, I think they could have done both well. So that was maybe not the trigger so much. But we've done Passive House with all ICF. And what we find, and this is plain old physics, is that the interior layer of that ICF, those 2.5 inches of foam, are pretty effective already, meaning that your concrete core is really disconnected from your interior space. And so you can't leverage it as thermal mass for the structure. It becomes worthless. It becomes just structure. But on the flip side, you use a little less concrete because ICF cores tend to be 6 inches, a pour like this about 8 inches. In this case, we decided we want to activate some of that as mass for the building. Can become a moderator for the building. And the slab and the walls are now both inside, and so they can work in that fashion. Last but not least, going back to Patrick's question here about the finished basement, if you do a exposed concrete wall, you can literally walk away. If you do an ICF basement, you have to drywall and fire tape it. You can't leave that unfinished for code reasons. So then you cut out that option of leaving it unfinished. Whereas with the concrete walls and the concrete slab, we can walk away with a raw space and get away with it. Those were the reasons. Yeah. Okay, there.
I was going to ask about forced air, if you could ever
forego that altogether with maybe floor heating?
Sure. Question was, can we forego the forced air and go to floor heating? Answer is yes, absolutely. And actually, the first passive house that I designed had in-floor heating, electric, have you note, not hydronic, and it didn't have a forced air system. Interestingly enough, the passive house, I think, is actually a model where a forced air system works much better. We sort of have it backwards. In conventional construction, where you have large heat loads and low temperatures surrounding you, a radiant heat system would make you much, much more comfortable. But in this particular model, where it's so well insulated, all you're really conditioning is the heat inside. That's where a forced air system shines, because it does that very quickly and efficiently. So it's sort of funny in that the traditional way of building is sort of exactly backwards. And we find these systems here are very cost effective. You could have done this with electric resistance heat, but we like the COP, the coefficient of productivity. Using a heat pump means we're squeezing energy out of the outdoor air. And we're doing that on the heating side with a factor of about 2.5, on the cooling side even over 3. So each kilowatt hour of electricity the system consumes gets turned into 2.5 kilowatts of useful heat. In electric resistance, it's 1-to-1. So we're actually getting a performance boost. We're using less energy if we use a system like this. And the beauty here is that it can cool and dehumidify. And in North America, in most places, you have some cooling and dehumidification need. And so we can kill two birds with one stone. We do it with one piece of equipment and go both ways on it. This is the first time, though, that we're using this particular system. So we'll have to report back how well that all works. It took quite a bit of engineering and working with the vendors to get to a duct layout that they felt was acceptable. Again, because these systems aren't really meant to supply a significant duct system. This, if anybody cares, it's a Fujitsu system. Yeah. Mitsubishi makes similar product. Yes.
So I think that the ducted systems aren't designed to go down to really low temperatures, but there are heat pumps that are designed to go down to
Yes.
-13 and stuff.
Yep.
Can you talk about your decision a little bit to go with the ducted models that don't go to as low temperature?
That's a great question, Rolf. So the question was, why did we go with a ducted heat pump and not a single split? Because a single split can actually provide a COP up to lower outdoor temperatures than the system that we chose. And the answer is quite simply the distribution dilemma. One of the things that we find is that single point source distribution, even in a passive house with a kick-ass building envelope, is problematic. Mostly on the cooling side, but somewhat on the heating side. So from a heat load perspective, we could have gotten away with providing one wall mount single split unit on the first floor and one on the second floor. But particularly on the second floor, when we have 3 or 4 bedrooms, 2 bathrooms, how is that heating and cooling going to find its way from that single unit into each bedroom? And the air that we're moving with the ventilation setup, the amount of air we're moving is relatively small. That's really not going to do it. On top of it, building code requires, in a cold climate, that you have a heat source in every room, in every habitable space that has exterior wall surface. So that's really not good enough. We can't meet the letter of the law, and we can't guarantee decent distribution. And I remember, on this channel here, a Passive House Alliance lecture, maybe earlier in the year, where a lot of people talked about using heat pumps in passive houses and reported on their findings in the field. And I think the consensus was very simply that single point source distribution does not work. All the projects that were shown that took that approach had problems, where people ended up having to prop doors open and put a floor fan in to try to move the hot or the cold around. And even then, it didn't really work. And that's something that we were sensitive to today from day one. And that's, I said, in our earlier models, we were working with in-floor heat, so a completely different model. But now that we're moving into this paradigm, we decided we're going to do proper distribution with it. Simple as that. And so we're taking a bit of a hit on the performance of the machine. But again, it's still providing a COP, which in our old paradigm with electric resistance heating, we had no COP. So for us, this is actually a step forward, even though it's not as good as some of the single split units. And believe me, Mitsubishi and Fujitsu have heard us in asking them for gearing this equipment more for the application or to the application. They're well aware that this group of people, the passive house designers in North America, can make very good use of their equipment. And they also understand that we want the ducted systems to be at the same level of performance as their single splits. It's a question of when they are able to turn that into a business model and provide products that are, better yet than this. But this is already pretty good. Yes.
What other resistance are you to with building code officials?
Sure. Resistance on building code officials. Yeah. On this particular project, the biggest hurdle was trying to site the home. Had nothing to do with Passive House, but the city, among the people who worked there, could not agree where it should be. And on the last day before excavation, they made us move the house 9 inches one direction on the site. That was the biggest hurdle that we ran into with code. It sounds stupid, but it was. Nothing on the Passive House side. And that's been our experience with other projects, simply because we're overbuilding. We're exceeding every bit of code that exists by such a fair margin that people usually don't question it. I will say on the ventilation distribution, I may have hinted at that earlier, what we're seeing there is the tubes that we use, the flex tubes, depending on how people look at them, they may collide with duct ordinances. Because I don't know, I don't fully understand all the specifics of it. And as a matter of fact, I have a working workshop, roundtable here in a couple of days with 30 people from the city of Minneapolis to discuss just that. But there's been some resistance, and I know this from other parts of the country, to code officials allowing that kind of product. I think a lot of it is to do with the fact that they simply don't know it, they don't understand what it does. But that hasn't come up as a problem here. Let me take one quick online question here. Patrick online has another question. Can you talk about the shade tree selection process as it relates to the shading of the building and desired solar heat gains? I can to some extent, Patrick. We had a landscape architect on board early on. We also are working with the landscape department at the college, again, for the educational component, and they will actually be executing the landscaping project. We didn't spend a lot of time looking at this, other than we wanted to make sure that they're deciduous trees, obviously, and that they're placed, not directly south in front of the building, but more southeast and southwest, and act as shade trees for the outdoor spaces. And we did include them in our model. Our shading model in the PHPP is actually fairly conservative, and we have some expectation that the building will outperform the model, because we're modeling the finished state with those trees in place, and also with the neighboring buildings that haven't even been built yet. So in the first few years, the building will likely outperform those calculations, because these constraints for the solar gains aren't there yet. Other than that, it was more an architectural or landscape design discussion. We wanted to make sure that the outdoor spaces are shaded in a way where you can sit on your deck out there on a nice sunny afternoon without getting baked. So it had less to do with Passive House, more with making a good site design.
With the ventilation system, what is the flow capacity on that unit? How many CFM might it deliver? And then secondly, adapting the ventilation to be a comfort distribution system, in effect, then the exhaust pickups are your return?
Yes, so the question is, what's the capacity of the vent system, and the exhaust pickups are the return, as you said it. So it's a 300 cubic meters an hour unit, nominal capacity, which is 200 CFM. The design airflow for the building is lower than that. I would say it's probably around 100, 120, something like that. I'm doing this from memory, don't hold me to it. And so the machine is going to run in a partial load scenario in everyday use, which is actually beneficial because it ups the efficiency of the heat exchanger. Now, this is one of those where we might be splitting hairs. We're starting with a machine that has a certified performance of, I think, 92% heat recovery, which is extraordinary already. So that's kind of the capacity of it. And there aren't any additional exhaust fans, obviously, in the house. So if we're exhausting a bathroom or we're exhausting from the kitchen, that goes through the unit. Everything runs through the unit, and there's a heat recovery on the way out. That's our winter scenario. Now, the machine itself has some intelligence, and it also has something called the summer bypass. So when you're coming up into the season where the house starts to heat up and you no longer want it to heat up, the ventilator itself can sense that and can decide at this point a heat recovery is actually not what I want to be doing, because I would be maintaining warmer indoor temperature than is desired. So it can open up a hatch and it can funnel in the outdoor air without doing a heat recovery on it. And that could happen at night, for instance. So you could do a nighttime ventilation with it. You can bring cold air in during the nighttime without doing heat recovery.
Or, I mean,
Yeah.
fall up in the summer, you could have that then dehumidified.
No, the machine. The question was, can you have it be dehumidified? No, the ventilator doesn't do any of that. This is an HRV setup. It has no moisture transfer potential whatsoever. So it doesn't do any of that. The dehumidification comes out of the heat pump system. Yeah. They're not ducted together. And that's an interesting one too. We did talk quite a bit with Fujitsu about that, because they can do that. It's possible to connect the heating, cooling, ventilation system together. The problem that you run into is that they have completely different CFM requirements. So while the ventilation system may be at 80 or 100 CFM, the heating cooling system, when it's running at full steam, may provide 400, 800 CFM of throughput. So they're not compatible. And that's where the story stops for me, because at that point you need to put in smart dampers and stuff like that, because otherwise you're going to start sucking on your ventilation setup, which could wreak havoc with the internals of that machine. And we decided to keep those two separate. And also, if you think about it, there's going to be plenty of times in the year where you're going to ventilate your house, but you're neither cooling nor heating. So running the heating and cooling setup during those periods of time and those additional fans that these units have makes no sense. So we, at least at this point, it's that paradigm for us. Those are two separate things. We can do it many different ways. We've done it anything from ground source heat pump, hydronic, electric resistance, now to forced air. We can talk about all these different systems, but I don't like to connect them. Bottom line, yeah. Your question.
Do you have any kind of a shutter system on your?
Oh, sure. Yeah, we didn't even get into that. So the question is, do we have a shutter system? And we do. We have an exterior aluminum Venetian blind system. I know you've seen these here before. We have one in our office too. So these are like indoor Venetian blinds, only bigger and made to live outside. They'll be installed on the east, west, and south facades. And they are controlled with two ways. We have a central smart control that you can program like a thermostat. So if working people should live there and they have to leave the house and they don't want it to heat up, they can run this like a thermostat and have the shutters come up and down. We'll also have overrides, and there's multiple ways you can do it. But depending on which room in the house you are, it might be a push button on the wall or it might be a handheld remote. So at any given point in time, you can ride them up or down manually in addition to that. Yeah. Yes?
Does this house require a condensing clothes dryer?
Yeah, good question. Question was, does it require a condensing clothes dryer? And it does, yes. There's not an opportunity for an exhaust-only device because the house will be too tight. And so that's the appliance that's going to go into this home. At the same time, our landscape design also provided outdoor line drying. So we have an area dedicated to that. And there's also a place in a bathroom where we're talking about indoor line drying. We pre-selected line drying element that can be lowered and raised from the ceiling to hang clothes. So that can work too, but there is a condensing dryer, yes.
What about the rest of the appliances?
Sure, rest of the appliances, there's an induction cooktop, which those are becoming more and more popular. It's just we wanted to keep all the combustion out of the house and not have a gas hookup. So that was a good choice. The range hood is recirculating, so it doesn't exhaust to the outside because that doesn't work. So the range hood's job now is cutting grease and odor. So you have basically a grease filter and a carbon filter in there, which is pretty standard stuff. And that's really it for the appliances. Everything else, refrigerator is standard refrigerator, dishwasher. We try to find the highest performing appliances in each category, but again, often that's owner driven. And In this particular case, there's a little bit of a sponsorship component going on. So who knows what they'll get donated to. But we have an outline of what these things need to be. So something like recirculating hood, condensing dryer, that's already spec'd. So they can choose from that pool. Yeah. Yes?
Do you have a manual accelerator on the exhaust in the kitchen area?
A manual accelerator, like a push button. Yeah, good question. So do we have sort of local control to boost the vent system? And we do. There's a push button controller in every bathroom. And on the main level, we have the main controller. So you can just walk up to that and put it in boost mode if you're cooking. And these boost mode settings, I think they're somewhat flexible, but for the most part, it's a 20-minute boost where the machine just goes into high. And that's pretty standard. That they're built. They all have some capacity. Even I have an older Venmar machine in my house, and while they're not at this level of performance, they even offer that. You can have push button controllers, 20, 40, 60-minute boost cycles. That's pretty standard in the industry. Yeah. We can connect it to indoor air quality sensors as well. This project doesn't have that, but a past project that we did, we forewent the boost buttons and we went to a completely automated system. So there are a couple of sensors measuring the return air, exhaust air quality, and based on that, it sets itself up for ventilation. And it's really quite interesting to see because I've given a number of tours at that home. You bring a bunch of people in there, you got a bunch of people breathing in there, and the system itself will start to kick into gear and start ventilating higher and higher to accommodate for that. Yeah. Yes.
So speaking of sensors, are you going to instrument one of the houses in the Crosse performance?
Yeah, good question. So are we going to instrument it? Yes, to the extent that we'll monitor the loads on it. No, the college itself has a department for, I think they call it architecture technology. And those students may go beyond what I'm aware of right now. But the electrical system at least is designed where all the circuits supply certain functions that are meaningful groupings. And then we're putting in an e-monitor, Powerhouse Dynamics e-monitor setup that's going to basically read all the loads back and forth, coming in and going out. So we'll at least have that. There may be more. We're talking about relative humidity and temperature, at least on every floor. But some of those things are going to be in the hands of the college that goes well beyond our sort of design component. And while we like access to it, that's really up to them how far they want to take it. Yeah, I just got the same question from somebody else. So Patrick, your question should have been answered then. All right, that's it, huh? Good deal. Well, thank you, everybody. This was great.